Hello and welcome all dear student in the next module of the topic solution. So in the last module what we have learned? We have learned about we have discussed the Raoults law, and before that we have discussed what is mean by vapor pressure. Vapor pressure of a solution or the vapor pressure is defined as the pressure exerted by the gaseous state of the substance when that gaseous substance is in equilibrium with its solid or liquid. So this is the definition of a vapor pressure. And then next to that we have discussed the Raoults law, and for that we have to consider the two volatile liquids. And as we know, volatility is the tendency of a liquid to goes into the gaseous state, that means into the vapor state. So if we consider the two volatile component A1 and A2 having partial pressure P1 and P2 and having vapor pressure P01 and P02, and for that the Raoults law is stated as the partial pressure of any component of the solution is equal to the multiplication of the mole fraction of that component and the vapor pressure of that component. So Raoults law mathematically written as, for the first component, if the P1 is the vapor pressure on the volatile component A1, then P1, which is equal to P01 into X1. This is the Raoults law for the first component. For the second component, the partial pressure on the second component A2 is equal to P2 is equal to P02 into X2, where X1 and X2 be the mole fraction of the volatile liquids or the volatile components A1 and A2 respectively. So from the statement of Raoults law, if we consider this is solution of two volatile component A1 and A2 having partial pressure P1 and P2, and this is the solution. So in this solution we have a two volatile component A1 and A2 having partial pressure P1 of the component A1 and P2 for the component A2, having vapor pressure P01 for A1 and P02 for A2, and having mole fraction X1 and X2 for A1 and A2 respectively. And therefore the Raoults law is stated as the partial vapor pressure of any volatile component of a solution is equal to the vapor pressure of that component multiplied by the mole fraction of that component in the solution. So mathematically it is written as P1 be the partial pressure on first component A1 in this solution, because in this solution it contains the two components A1 and A2. When we mix that two volatile component A1 and A2, it forms a mixture, and therefore the pressure on partial pressure on A1 is P1, vapor pressure of A1 is P01, and the mole fraction of A1 is X1, such that A2 is the second component having partial pressure P2, having vapor pressure P02, and having mole fraction of that A2 is X2. And from this the Raoults law, it can be stated as the partial vapor pressure of any component of the solution is equal to the vapor pressure of that component multiplied by the mole fraction of that component in the solution. So this is the statement of Raoults law, and mathematically it is written as P1 is equal to P naught 1 x1 and P2 is equal to P naught 2 x2. But if we consider this solution having two volatile liquids, then what is the total pressure? The total pressure of the solution is according to the Dalton's law of partial pressure from our 11th standard topic, states of matter. In the topic states of matter, we have given the Dalton's law of partial pressure, and from that Dalton's law of partial pressure, the total pressure of any one of the solution is equal to the sum of the partial pressures of each component of that solution. And therefore, in this solution, they are having a two volatile component A1 and A2, and therefore the total pressure of the solution is the sum of the pressure due to first component and the pressure due to second component. So the total pressure P of the solution is equal to the partial pressure due to the first component plus the partial pressure due to the second component. That means the total pressure P is equal to P1 plus P2. If we put the value of P1 plus P2, P1 is equal to P01 x1 plus P2 is equal to P02 x2. If we put the value of P1 and P2 in this equation, then P is equal to total pressure, which is equal to P01 x1 plus P02 x2. But as we know, x1 and x2 be the mole fraction of the first and the second component, and as we know, x1 plus x2 is equal to 1. The total mole fraction is equal to 1. x1 plus x2 is equal to 1, and therefore here x1 and therefore x1 which is equal to 1 minus x2. x1 which is equal to 1 minus x2. If we have to put the value of x1, 1 minus x2 in this equation, then we get here P is equal to P01. What is the value of x1? 1 minus x2 plus P02 x2, because here x1 which is equal to 1 minus x2, and if we simplify this, then we get the Raoults law for non-volatile liquids, because both A1 and A2 are the non-volatile liquids, and therefore here we have P01 minus P01 x2 plus P02 x2. Here x2 both are common, and therefore here we get P01 in bracket P02 minus P01, and here we have a x2, and therefore the total pressure P is equal to here P01 plus P02 minus P01 x2. So this is the Raoults law. हा आपला काय आहे Raoults law, and therefore because of the pressure P01 and P02 are constant, if we plot a graph, of a P means the vapor pressure versus the mole fraction, vapor pressure versus the mole fraction, then it looks like, that means you have to see a graph of a vapor pressure versus mole fraction here. This is the graph of vapor pressure versus a mole fraction. P1 be the partial pressure of first component, P2 be the partial pressure of second component, and P be the total pressure due to the first and second component. So, if we plot a graph of vapor pressure versus the mole fraction, then it looks like this. This is the graph of a vapor pressure versus a mole fraction. So, this is the statement and derivation of the Raoults law for both the liquids if they are volatiles. If both the liquids are volatile, then what is the total pressure? The total pressure, which is equal to P01, means the partial pressure for the first component in the bracket P02 minus P01. Sorry, here we have a plus sign P01 plus here P02 minus P01 x2. या दोघांमधून आपण x2 कॉमन काढलेला आहे, P02 पहिल्यांदा लिहिलेला आहे मायनस P01 इथं पहिल्यांदा लिहिलेला आहे P05. So this is the total pressure according to the Raoults law. So next to that we have a next concept, that is what is mean by ideal and non-ideal solution. What is mean by ideal and non-ideal solution? So for that, here if we have considered two volatile liquids, here we consider two volatile liquids for the ideal solution. What are the ideal solution? And for that, here we consider two volatile liquids. This is the liquid A, this is the volatile liquid A, and this one be the volatile liquid B. So this is the volatile liquid B. And if we mix these two solutions, then means if we mix these two liquids, then it forms a solution of A and B. If we mix this solution, then it forms a solution having the volatile component A and B. So here, if we consider the volatile liquid A and volatile liquid B, both are volatile, therefore they both having a vapor pressure. Volatile liquid, they are readily goes into the vapor state, and therefore they exert a pressure called as a vapor pressure. And if we consider the solution of these both volatile liquid, then if we have a solution, then in that solution three type of interactions are possible. This is the volatile liquid A, and therefore in this A only AA interactions are possible. In this B only BB interaction are possible. And if we consider these, then here we have three type of interaction: AA interaction, AB interaction, and BB interaction. Suppose A is here, A is a solvent and B is a solute. A is a solvent and B is a solute, and if we add this solute in this solvent, then here AA means, here A is a solvent, means solvent solvent, solute solute, and solvent solute interactions are possible when a solution is formed. When a solution is formed, then they are having a three type of interaction: solute solute interaction, solvent solvent interaction, and solute solvent interaction. And if if the strength of AB means a solute-solvent interaction is equal to the strength of AA and is also equal to the strength of BB. That means if in a solution the strength of AB interaction means a solute-solvent interaction is the same as that of the solute-solute interaction and the solvent-solvent interaction, then that type of a solution is called as a ideal solution. Ideal solution is one in which the strength of solute-solvent, solute-solute and solvent-solvent interactions are same. Means the strength, the intermolecular force of interactions are same for solvent-solvent, for solute-solute and for solute-solvent, then that types of solutions are called as ideal solutions. Ideal solutions are the solutions in which the interaction between solute-solute, solute-solvent and solvent-solvents are same. Then these solutions are called as a ideal solution. These solutions are called as a ideal solution in which the interactions, all the interactions are same. All means solute-solute, solute-solvent and solvent-solvent interactions. Means the strength of that interactions are same, are called as the ideal solutions. Then what are the properties of ideal solutions? First, the ideal solution which obeys the Raoults law. Ideal solution which obeys the Raoults law. Means here the P1 which is equal to P01 x2 and P2 which is equal to P02 x2. Ideal solution is one which obeys the Raoults law. Ideal solution which obeys the Raoults law for the entire range of pressure and temperature. Here, when the ideal solutions are formed, all the interactions are same and therefore no heat is evolved or absorbed. Therefore, delta V is equal to 0. Delta V, that means, delta H mix. Delta H is equal to 0 because before mixing the solution, the heat evolved or gained is the same because the interactions are the same. Therefore, the delta H means the change in delta H mix is 0. If the interactions are the same, then the volume of the solutions are also same. Before and after mixing the solution, the volume is also remains same. Ideal solution means the solution in which all the interactions or the strength of all the interactions are same. Ideal solution which obeys the Raoults law, or the solution which obeys the Raoults law called as the ideal solution, and no heat is evolved or gained before or after mixing the solution. Therefore, the change in enthalpy is 0 and therefore the change in volume is also 0. The example of the ideal solution is a solution of benzene, and toluene. A solution of benzene and toluene are the examples of the, or there are some examples of the ideal solutions. In that, one of is benzene and toluene. So, the ideal solutions are the solutions which obeys the Raoults law over the entire range of temperature. For the ideal solution, change in enthalpy is 0, change in volume is also 0, and it obeys the Raoults law. For example, benzene and toluene. So, this is all about the ideal solution. And for the ideal solution, A-B interaction is equal to the AA interaction is equal to the BB interaction. So, this is all about the ideal solution. So, next to that, what are non-ideal solution? Or that means non-ideal solutions are called as a real solutions. Non-ideal solutions are also called as a real solution. So what is the difference between ideal solution and non-ideal solutions? For ideal solution, here the strength of interaction between solute-solvent, solute-solute and solvent-solvent are nearly same. The interaction, when they form a solution, then the interactions means the force of attraction between solute-solvent are same as that of the solute-solute and solvent-solvent molecules. But for a real solution, that means for a non-ideal solution, the interaction between the solute and solvent, they may be greater or they may be lower than the solute-solute and solvent-solvent interactions. For a non-ideal solution, there is a difference between the solute-solvent and solute-solute and solvent-solvent interaction. It may be higher or it may be lower than these interactions. So, what are the properties of a non-ideal solution? The first one, a non-ideal solution, it does not obey. It does not obey the Raoults law. It does not obey the Raoults law. That means either the vapor pressure of the solution is lower than or the higher than that of the pure component. Means the vapor pressure of the solution of the non-ideal solution, that means the real solution, is either greater than or the lower than that of the pure components. And therefore here there is some deviations from the Raoults law. That means a non-ideal solution does not obey the Raoults law. It does not obey the Raoults law. That means for a non-ideal solution, the interaction between solute and solvent molecule is either higher or lower than that of the pure component, and therefore here the enthalpy change is not equal to 0 for the non-ideal solution, and the delta V change in volume is also not equal to 0 for the non-ideal, that means a real solution. So here there is some deviation because it does not obey the Raoults law. Therefore there is some deviations from the Raoults law, and therefore for that the two cases arises for a non-ideal solution. For a non-ideal solution here there is a deviation from the Raoults law because it does not obey the Raoults law. That means P1 is not equal to P01 x1. It is higher or lower than that of. So if these are the two cases, that means here if AB interaction is greater than AA and BB interaction, if the interaction between solute and solvent molecule is greater means the force of attraction between the solute and solvent is higher than the solute molecule and solvent molecule, and therefore there is a strong interaction or the strong intermolecular force of interaction between A and B in this first case. This is the first case which shows the deviation from the Raoults law, because it does not obey the Raoults law. Raoults law, ideal gas solution. The solution which obeys the Raoults law called as ideal gas solutions, means all the interactions are same. But if the interaction is greater or lower than the ideal, then it shows the deviation from the Raoults law. In the first case, if AB interaction is is higher than the solute-solute or solvent-solvent interaction, then in that case the escaping tendency of the AB it get decreases. That means here when the solution is formed, then this interaction is very strong, is greater than this interaction. That means the escaping tendency, it does not readily goes into the vapor state, because the force of interaction between A and B, AB bond is strong. Strong means it does not readily broke down, and therefore the escaping tendency here, the escaping tendency decreases, and decreases. If the escaping tendency decreases, then at that time the vapor pressure also decreases. At that time the vapor pressure also decreases. At that time the vapor pressure also decreases. And therefore here, that means the vapor pressure. This is the graph of ideal gas solution, but there is some deviation for the non-ideal gas solution. Means if the vapor pressure decreases, here if the vapor pressure decreases, that means this is an ideal curve and this shows the negative deviation. It shows the negative deviation, because the graph, it is the ideal gas solution which obeys the Raoults law, but there is some deviation from the Raoults law. If the interaction between these two molecules, solute solvent, are stronger than the solute solute and solvent solvent interaction, then at that time it does not readily goes into the vapor state. Therefore the escaping tendency decreases, and at that time the vapor pressure is also decreases. That means here P1 which is greater than P01 x1 and P2 which is greater than P02 x2, because it does not obey the Raoults law. Vapor pressure is lower than the partial pressure here. The vapor pressure P01 here for the negative deviation P02 x2, P1 is equal to P1 is less than P01 x1 and also P2 is less than P02 x2, and here therefore the change in enthalpy, the change in energy is less than 0, and therefore the change in volume is also less than 0. Why it is so? The change in enthalpy is less than 0 and the change in volume is also less than 0 because it shows the negative deviation. In case first, here we have to study the negative deviation from the Raoults law. When there is a strong interaction between the solute and solvent molecule, when there is a strong interaction between the solute and solvent molecule, and therefore the change in enthalpy is less than 0. And at that time the change in volume is also less than 0. This is for the negative deviation. In case second, if this interaction is lower than the solute-solute and solvent-solvent interaction, then what happens? The escaping tendency is increases here. What happens in this case? In the second case, what happens? If the interaction between solute and solvent is lower than the AA and PV interaction, means solute and solvent interaction, then what happen? The escaping tendency increases because there is a weak intermolecular force of attraction between A and B, and therefore it readily goes into the vapor state, and therefore the escaping tendency increases. And if the escaping tendency increases, then the vapor pressure also increases. Then at that time the vapor pressure also increases. That means it shows the which type of deviation. If the vapor pressure increases, then it shows the positive deviation. It shows the positive deviation from the Raoults law. That means P1 is greater than P01 x1, and also P2 is greater than P02 x2. Therefore, at that time, suppose this is a dotted line, this is the ideal gas equation. Has a graph, it shows the negative deviation. Why it shows the negative deviation? Because the vapor pressure decreases. But if the bond is weak, then escaping tendency increases. If escaping tendency increases, then it readily goes into the vapor state, and therefore the vapor pressure increases, and it shows the such deviation of the law. एकाच ग्राफ मध्ये मी म्हणजे एकाच फिगर मध्ये 3 ग्राफ एक्सप्लेन केलेले आहेत. तुमच्या बुक्स मध्ये ते वेगवेगळे दिलेले, ते परत बघायचे तुम्ही. वेपर प्रेशर वर्सेस मोल फ्रॅक्शन हे जे काही ग्राफ आहेत ते. Ideal solutions are the solutions which obeys the Raoults law, in which all the interactions of the solutions are same, and a non-ideal solutions does not obey the Raoults law. It shows the deviation from the Raoults law. Why? Because the interactions are different. Either the interactions are higher than the pure component or lower than the pure component. If the interactions of the solute solvents are higher than the pure component, then it shows the negative deviation, and if the interactions are lower than the higher concentration than the pure component, then it shows the positive deviations. So, and actually no gas is perfect, or the no substance is a perfect real. So here the ideal, non-ideal solutions are also called as a real solution. Non-ideal solutions are called as a real solution. So all these about the Raoults law, ideal solutions and non-ideal solutions. So you have to see carefully this video, compare it with the notebook figures which we have discussed here, and if you have any doubt, then ask me on our meeting. Okay, then in today's lecture we will stop here. We will meet in the next lecture. Till then, thank you.